Okay. All right, so let's start again with me asking you if you have any questions that you want me to cover, or should I just go through the material of chapter 3, which was what you were supposed to be working on this week?
I have a question.
Okay.
It's quiz number 2, question number 1. I think it was like the resistance through a circuit.
Okay, so I've been sending out messages, stop taking the quizzes.
Yeah, I just
They
got
don't
that.
work. I actually spent a couple of hours trying to fix them, and I really don't understand why they're not fixed, and I just apologize for it. If you want to look at the quizzes just to see the type of questions and make sure you know how to do them, great. If you want to check your answer with me, you can do that, but they're not, when you put in the right answer, the quiz tells you it's the wrong answer. So I know that's frustrating because you're like, no, I'm sure it's the right answer, right?
Yeah.
Yeah. So here's a lesson. Develop confidence in yourself. If you're sure you have the right answer, then you should say, I'm right, and this stupid computer is wrong, or the book is wrong, or the teacher's wrong, and you will have the confidence to back up why you think you're right and someone else is wrong. Now, of course, I wouldn't recommend going through life always thinking you're right. You know, you got to be open to like, oh, well, maybe I'm wrong. But if you really think that your method is correct and you've gotten the right answer, you probably did. So anyway, if it's frustrating, just stop taking the quizzes. If you want to just look at them to see what types of questions are there that you should be able to answer. But that's all. You don't really have to do that. The quizzes are more just for extra help. Everything that you need to know is in the reading and the homework. So it's not going to hurt you not to take the quizzes, but sometimes it'll help. All right? Clear? And don't worry about the grade on the quizzes. I'll just give everybody, full credit on the quizzes. Okay, any other questions about a problem that you might have had trouble with or a concept? All right. So let me back up just a little bit, because when I watched the video last week, I realized that I didn't make as much of a distinction as I had wanted to about the difference between an ideal source, an independent source, and a dependent source. I didn't say anything wrong, but I didn't make as clear a distinction as I had wanted to, so I want to do it right now. The definition of an ideal source is that it's something that delivers energy to a circuit, and it does it either in the form of a voltage, and so I'll show that as Vs, or a current. And I'm actually intentionally trying to make these small letters because I do want the possibility that they can vary with time. They don't have to be constant, these sources. In fact, when we get toward the end of the semester, we'll be looking at alternating current, which does vary with time, and so sometimes you'll see a little symbol like that, which tells you, oh, this is not constant, it actually varies with time, and it does it in a sinusoidal way. Similarly, you might see something like that, which tells you that the current that this is delivering is varying with time. So it doesn't matter whether it's constant or not. What matters is that it delivers whatever it says it does, whether it's a constant value or maybe it varies with time like that. Whoops. Maybe it's 10 sine 4t volts. Well, at any particular time t, you know what the voltage is, because you just plug t in and there you got it. And it doesn't matter what the current is. It will give you this voltage regardless of the current. In other words, regardless of what it's hooked up to. So if I were going to write out the definition in words, I would say an ideal voltage source delivers its voltage regardless of the current through it. And another way to say regardless of the current through it, I could have phrased it regardless of what it's hooked up to. Okay, so that's what it means to be ideal. And then, of course, for the current source, it's the dual definition. Okay, I think I mentioned the word dual before. Does anybody remember what I mean by dual? So you can have two circuits, and they are mathematically equivalent if for every voltage in this circuit, you've got a current here. For every resistor in the circuit, you consider it a conductance in this circuit. Any inductor is considered a capacitor. So you've kind of got these dual elements. So if I were going to write the dual of this sentence, what I would do is I would change the word voltage to current. And the word current to voltage. So an ideal current source basically delivers its current, the current that it says it delivers, regardless of the voltage across it. In other words, regardless of what it's hooked up to. That's what it means to be ideal. That is the definition of ideal. Absorb it now. Raise your hand when it's absorbed completely into the depths of your soul. Okay, I don't even see one hand up. Okay, but you'll work on it at home, right? This is the definition of ideal source. Both independent sources and dependent sources are ideal. Both of these are ideal. What I'm going to further define is in addition to this idea. Okay? So an independent source, it really looks the same as these, will deliver, let me put the sentence, an independent source delivers the voltage, or if it's a current source, the current, I'll put it in parentheses, independent I don't like the way I'm phrasing it. Let me make it a little less awkward. An independent source delivers its voltage regardless of any current or voltage elsewhere in the circuit. In other words, not only is the voltage of the source or the current of the source independent of the current through it, but it's also independent of any other voltage or current somewhere else in the circuit. Okay, so, and for a current source, it's going to deliver this current regardless of the voltage across it, because it's ideal, and additionally regardless of any other voltage or current in the circuit. And of course, that's what a dependent source is that it does depend, the voltage or the current it delivers is dependent on some voltage or current elsewhere. I'm going to put that in capital letters because that's the key. In other words, it can't be dependent on this because it's ideal. We already said that a dependent source is ideal. So the current it delivers will be independent of the voltage across it. But it's going to depend on some current or voltage elsewhere. And then we agreed that we were going to show those type of sources with a diamond, and that there were 4 basic types, right? You could have a current-controlled voltage source, a voltage-controlled voltage source, or you could have, what? A current-controlled current source, or a voltage-controlled current source. And that's where we got into thinking about the units of the constant. So let's say there's, and I said, it could be hooked up to anything, but there's some resistor somewhere in that mess of stuff it's hooked up to, and I'll call the current through that resistor IR and the voltage VR. So if this were a current-controlled voltage source, then it might look something like that, where the voltage it delivers is K times this current here in the circuit. This is where you're going to come into pitfalls. You're going to look at this and think, oh, it's a current. And it's not. This is not a current. This is a voltage. Because this is a voltage source and it's delivering a voltage. You can tell by the picture. Now, the voltage it delivers is whatever this current is times K. So that's where you get into the idea that K has to have units. And so the units of K have to be, well, if we're ultimately going to get volts here, and this has units of amps, K better be volts over amps. So sometimes it has units. Sometimes constants have units, and sometimes constants don't, right? Like, what's a constant that you come across in physics that has units? Pretty much all of them, right? The universal gravitational constant. I don't know. There's a lot of constants. Gravity, it's a constant, but they have units, right? Are you familiar with any constants that don't have units?
Mu, the coefficient of friction.
Yeah, good, thank you. Mu, the coefficient of friction. That's a great example, and thank you for coming up with it, because I was blanking out and couldn't think of one constant that didn't have units. But they're out there. So this one's not one of them. This one has a unit. But if it were a voltage-controlled voltage source, then this constant doesn't have units. Or I suppose you could call it volts over volts, but that's really no units. All right, so anybody want to ask a question about this before I go on to the next topic?
I'm still not sure how the two are different, ideal and independent.
Well, good question. Independent, think of it this way. An independent source is an ideal source, and it's not a dependent source. I think that's the best I can do. A dependent source is ideal. Both of these are ideal. And furthermore, a dependent source does depend on some voltage or current somewhere else in the circuit. An independent source doesn't. I mean, you can actually take these definitions and just negate them. So like an independent source, the voltage or current it delivers is not dependent on some voltage or current elsewhere in the circuit. So if you just add the word not here, then this becomes an independent source. Or if you take this definition and you want to make it dependent, then you just would say it delivers its voltage or current depending. So you'd have to change the word regardless to depending. Anyway, yeah, I probably shouldn't have gone down that road, but do you make sense?
What about like if it's up to a regulator?
Okay, so you're probably thinking about the real world. And I'm not in the real world right here. I'm in my little fantasy ideal world. How close does my fantasy model the real world? And that's where you get into the whole concept of the model of a real device versus what it actually does. We're talking about mathematical models. And in fact, this is not a very good model for what really happens in the real world. But it's a good first approximation. And engineers are pretty notorious for you know, doing approximations, and if you're somewhere within maybe 50% accurate, good enough. Maybe 50% isn't enough. Maybe you need to be 20%. Really, it depends on what you're doing. If you're flying an airplane, you probably want to be more accurate than that. So anyway, the point is that these are models, and so we'll talk as we go through the semester how close our models do predict actual currents and voltages. But for now, just accept the definitions and let's work with them. All right? All right. It turns out this is not the greatest model, but if we put it together with some other things, it'll become much closer to reality. And so that's where we're headed. Okay, so the topics for this week were the concepts of, I think, parallel. Well, now I'm just going to make the checklist here. You should have learned Kirchhoff's current law, Kirchhoff's voltage law, what it means to be parallel, series, and equivalent. And then voltage division and current division. And in this concept of equivalence, you should be able to calculate equivalent what's the word? Resistances for circuits in parallel and series. Okay, and I think you learned that in physics, so hopefully it's not totally new. But, okay, the idea of Kirchhoff's current law, let's just do that real quickly. The way it mathematically looks is you've got the summation of all the currents is equal to 0. Okay, well, what do we mean by all the currents? If you have a node and you've got branches coming into that node, and you show the currents, maybe I1, I2, I3, and I4, what this is saying is that all of the currents coming into a node will sum up to be 0. And so in this case, since I've only got 4 branches coming into the node, I is going to go from 1 to 4. But a lot of times on these summation symbols, you just let the person figure out what the starting point and end point is, because it's usually obvious. But if you like to actually see it there, go ahead and put it there. So in this case, we've got summing up the, oh, and this should be I sub I, because it's I sub 1 plus I sub 2 plus I sub 3 plus I sub 4. You all know what these summation symbols mean, right? So that's Kirchhoff's current law. And it's a basic law of physics, really. And what physical phenomenon is it based on? Why is it that when you sum up all the currents coming and leaving the node, you should get 0? Anybody know why that's true? I think you got it. Say it again.
Nodes can't hold charge.
Nodes can't hold charge? Yes, that's exactly right. You cannot accumulate charge at a node. So if a charge comes in, it's got to go out. It can't store it there. And does it matter if I consider current leaving the node positive rather than negative? Is it going to make a difference in the equation?
As long as you keep them on the same.
Yeah, as long as you're consistent. Personally, I like to just always say, okay, currents leaving the node are positive, just because it keeps like kind of a consistency in the way I do my problems, but it really doesn't matter. But if I did it that way, then I would have minus I1 plus I2 plus I3 minus I4 is equal to 0. And there's my equation for Kirchhoff's current law at that node. If I somebody that says, no, I want to take the currents coming into the node as positive, in which case the equation would look like this. I1 minus I2 minus I3 plus I4. And then you might look at it and say, well, that's a different equation. Is it? No. Yeah, it's not a different equation. You just multiply the whole thing by -1, and we've got that equation back. So it's the same equation. All right. And Kirchhoff's voltage law basically is the dual of Kirchhoff's current law, but instead of a voltage, instead of a current, we'll have a voltage. So some kind of voltages are summing up to 0. What voltages are summing up to 0? What's the dual of a node? Anybody have any idea? The dual of a node is a loop. It's when you take a walk around the circuit and you start and stop at the same place. That was a definition from, I think, chapter 2, maybe chapter 1. But a loop is just a path in a circuit where you start and you stop at the same spot. So maybe, we've got a circuit with 3 resistors, and I'll call this loop, well, it's the only loop there is. Sometimes if you had like something like this maybe, then I'd call it the right loop. This would be the left loop. So you do have to learn to identify it so that people know what you're doing. So if I'm going to do Kirchhoff's voltage law in the right loop, then I would have to sum up all the voltages, so I have to show them. I'll show. And in this case, I actually goes from 1 to 3. I don't know why I skipped 2, sorry. And it would be, if I go, it doesn't matter which direction I go. If I go this direction, I'll have plus V1 minus V3 plus V2 is equal to 0. If I went in the other direction, it would be minus V1 minus V2 plus V3 equals 0. But of course, that's the same equation. You just multiply it with -1 and you've got the same thing. Okay, great. So parallel. Okay, here's the definition of parallel. 2 branches that are between the same 2 nodes are in parallel. That's the definition. So these are obviously in parallel. But sometimes you've got some configurations where it may not look like it's in parallel, but it is. Is that in parallel?
No.
Yes, because it meets the definition. 2 branches that are between the same 2 nodes. In other words, they share the same voltage, right? Because we know that the voltage between 2 points is always going to be the same, no matter what path you take. So if you take this path, the voltage will be the same as this path, and so we call that parallel.
So as long as they're connecting to the same 2 nodes.
Yes, any branch between the same 2 nodes. Okay, so that's one way to think about it. Another way you can think about it is 2 branches that have the same voltage. Okay? Oh, by the way, we talked about what the physical basis was of Kirchhoff's current law. What's the physical basis for Kirchhoff's voltage law? Why is it true that if I start and stop at the same node and I add up all the voltages that I go across, or voltage drops, whichever it is, I come up with 0. Why is that? Anybody want to guess? Louder? Yeah, because the energy to go from a point to the same point is 0. And remember, that's what voltage is. It's the amount of energy it takes to go from point A to point B. So if you're going to point A to point A, it's going to be 0. So that's why. And it also has to do with the fact that voltages are from electrical forces which are conservative. So that's why it doesn't matter whether you just go from point A to point A and you don't travel anywhere, or you go all the way around here or go to the moon and back. It's going to be the same voltage and it's going to be 0. Okay, so good. So now we know what parallel is. The definition of series is 2 branches that have the same current. 2 branches that have the same current. Which is actually, let me add that here. These two, R1, R2, and R3, okay. R1 and R2 are still in parallel, aren't they? Right, there's still 2 branches between the same 2 nodes. They were also in series before I added this R3. Now they're not. Because series, the definition of series is that 2 branches that have the same current, none of these have the same current. If I added an R4, let me add it, whoops. Let me add it here. Now, do you see any branches that are in series? Yeah, R3 and R4 are in series because they share the same current. There's nowhere for this current to go other than up to R4 because there's no other branch there. It's a little bit more obvious if I did it like that, right? If I put R4 here, then it's like, oh yeah, those are in series. But you've got to be able to recognize whether or not something's in parallel or series, even when it's kind of, you know, off from what you expect. Yeah.
So will we consider R1 and R2 are parallel with R4 and R3?
Yes. You could say that R1 is parallel with the branch that contains R3 and R4. Yeah, so these 2 are in parallel with R1. Okay, and then I'm assuming you know the formulas for calculating equivalent resistances for parallel and series. So the equivalent resistance for R3 and R4, in other words, the equivalent resistance between these 2 nodes in this branch is R3 plus R4. In fact, let's talk about that. I'll just do 3. Okay, so here we've got 3 resistors in series. Oops. And, you know, let's say, okay, so this is node A and this is node B. Here's a question. Can I have an equivalent circuit, an equivalent branch here between A and B that just has 1 resistor? And the answer is yes. And it's equal to R1 plus R2 plus R3. And the way you prove it is by this concept of equivalency. Okay, this is kind of a difficult concept, so let's make sure we get it. 2 circuits are equivalent if their voltage current characteristic is the same. That's the definition. Maybe I'll write it down. So equivalent is circuits are equivalent when they're okay, so how can we make our voltage current characteristics the same in both these cases? Well, let's label a current and let's label the individual voltages across each of these resistors. And let's see if the mathematical relationship what the mathematical relationship is between these two, and what it would require for these to be the same voltage current characteristic. Well, the total voltage between points A and B is what? For this picture. Isn't it just V1 plus V2 plus V3? And by Ohm's law, we can see that V1 is equal to I times R1, because that's, remember, the voltage current characteristic tells you the relationship between the current and the voltage for that device. And we saw last week that for a resistor, V equals IR, and of course, we need to know the polarity on V and the direction of I, and the way I've set it up is consistent with the voltage characteristic being V equals IR. So V1 is I times R1. Let me put it underneath here, because that's what V1 is. I times R1. V2 is I times R2. And V3 is I times R3. And if we factor out the I, we've got R1 plus R2 plus R3. So here is the voltage current characteristic for that configuration. Now let's see what's the voltage current characteristic for this configuration. Well, we've just got one resistor, so the voltage across it is going to be equal to IR. For these two equations to be the same, Req has to equal R1 plus R2 plus R3. You know, I shouldn't have put this subscript here, I'm realizing, because really I'm measuring the voltage between the same 2 points. So I could just call it V like I called it up here. So in both cases, the voltage current characteristic, well, in this case it looks like this, in this case it looks like this. In order for them to be equivalent, Req has to equal R1 plus R2 plus R3. So that's how this formula was derived, you know. So resistors that are in series can be replaced by an equivalent resistor, which is just the sum. You can go through the exact same kind of proof for parallel, but what you get there is the equation's going to look like this, that the equivalent resistance is related to the others by this kind of thing. And if you remember that the reciprocal of resistance is conductance with a G, okay? That's just a definition. Conductance is just the reciprocal of resistance. That's what conductance is. So if I just put this in terms of conductance instead of resistance, then we see that for resistors in parallel, all you have to do is add up their conductances. For resistors in series, you add up their resistances. So you see how those dual concepts come out? So that's a way to remember it. If you can remember that if you have resistors in series, you can get the equivalent resistance by adding up their resistances, then you can remember that in order to get the equivalent resistance for resistors in parallel, you add up their conductances. Because parallel and series are dual concepts, and resistance and conductance. concepts, our dual concepts. Okay. Okay. All right, now I want to talk about voltage division and current division. And I think what I'm going to do is do a problem that we need to use those concepts in, and that way you'll get some practice doing it. Okay, first of all, let me say that voltage division is the dual of current division. So, what it means, here's what voltage division is. If you have a voltage, and I'll show it as a voltage source, doesn't have to be, but if you have a voltage which is being divided amongst resistors in series, right? Because you got this voltage, and then this resistor, R1, let's say R2, R3, and it could go up to 100, Rn, I'll say. They'll have different voltages, but the sum of them, of course, will equal Vs. What if I know what Vs is, and I'm really only interested in finding the voltage in one of these branches? There's a formula, and it's called voltage division. Here's how the formula works. Which one do you want to find? 1, 2, 3, 56?
3.
3. Okay, oh, let's say this is 100. Okay, let's find the voltage across R3. So we know that the voltage across R3 is going to be some fraction of the total. Some fraction of the total. That fraction is going to be the voltage across R3 divided by the sum, I'm sorry, it should have been the resistance, not the voltage. The resistance across that branch divided by the sum of all the resistors. That's the formula. Fun to make sure I had it right because the dual is a little bit different. So the dual of voltage division is current division. And there, instead of having resistors in series, well, instead of having a voltage source, what do we have? We'll have some kind of current. And the current is going to be divided among resistors. But, these resistors aren't dividing current. They all have the same current. So they have to be in parallel. In order for resistors to divide current, they have to be in parallel. So let's say we have 100 resistors in parallel. I'm just showing 2 of them and then the last one. And we've got a current coming into them, Is, and we want to know what the current is in the ith branch. So it could be the 2nd, the 3rd, the 4th, the 56th, the 100th, whichever branch you're interested in finding the current in. You can use a formula that we call current division, and let's do the 56th branch, even though you're not really seeing it here. What it's going to be is the conductance of that branch. So it's going to be 1 over the resistance of that branch divided by the sum of all the conductances. So it would be the sum of 1 over all of those resistors. Okay, so there's voltage division and current division. Let's do a problem. good, it's got a lot of different things that we are learning here too. Okay, so here's one circuit, oops. And then here's an equivalent circuit. And so I want to know what is the value of R1 and R2 such that these two circuits are equivalent. Well, it looks like we're going to have to first figure out the equivalence in that branch, which is what? You just add them, right? Because these are in series, right? Because it's got the same current. And so that's going to be 18. And then 18 in parallel with 9. Let's see. So 18 in parallel with 9 is going to be 1 over 18 plus 1 over 9. You agree? Okay, so multiply by 18. You got 18 over 3, 6. Check my math. Yeah, I think that's right. Okay, so R1 has to equal 6 ohms. Okay, R2, okay, so R2 is the combination of these three. So first let's take these two and figure out that parallel combination. So we're trying to figure out the equivalent combination of 8 in parallel with 12. So let's see, it's going to be 1 over 8 plus 1 over 12, right? Oh, I didn't want that. 8 in parallel with 12 is going to be 1 over 1/8 plus 1/12. Everyone, so what's that going to be? 24 over 5, yeah. Yeah, that's not a very nice number. I thought the numbers were better. Well, and then we've got to figure out the equivalent combination of 24 over 5 with 24. So it's going to be 1 over 5 over 24ths plus 1 over 24ths. So that's 6 over 24, 24 over 6. Oh, it turns out to be nice. It turns to be 4. I think I did my math right.
Yeah, 4.
Thank you. Okay, so R2, so that's that much, just figuring out the equivalent resistances. But now there's a harder part of the problem. In figure, these are both equivalent, and the currents, IA, are the same, and the currents IB are the same. So, because these are equivalent circuits, we want to use this fact to determine the values of V1, which we see here, and I2. I'm sorry, I put the 2 in the wrong place. This is I2 here. Okay, so now we're asked to find V1 and I2. Okay, so now that we know R1 is, what did we say R1 is 6, and R2 is 4, I'm going to erase that part of the board so that I can have some room to work. Anybody got some bright ideas? Well, if we do, let's see, if we do Kirchhoff's voltage law around this loop here, I think we can find IA. So let me do it. And by the way, when you do equations, I want you to tell me what you're doing. So I want to see Kirchhoff's voltage law around the left loop. Actually, I'm going to call it a mesh. Anybody know what the difference between a mesh and a loop are? A mesh is the smallest path you can have. In other words, there's no loops inside a mesh. So, for instance, this perimeter is a loop, but it's not a mesh because you've got 2 loops inside it. This is a mesh because you don't have any loops inside it. So a mesh is like the smallest part that you can have for a loop. Okay, so I'm going to use the word mesh here. So I'm going to do Kirchhoff's voltage law around left mesh. And so, let's see, if I go clockwise, I'm going to get minus 27 plus, okay, for now I'm just going to label this VR, because I'm not quite sure what it is, VR plus 3IA equals 0. Now I'm going to look more closely at the VR. Well, look, by Ohm's law, VR is equal to IA times R1. So I'll put that in. IA times R1 plus 3IA equals 0. And we know R1 is 6. So 6 plus 3 is 9. And so IA is 3 amps. Okay, now that I know what IA is, and it's the same up here, let's figure out I2 by using current division. Right? Now that we know that IA is 3 amps, we can go back up to this picture, and we've got, oh wait, no, I need to know IB. Well, because IA really isn't coming into the 3 resistors in parallel, it's also going here. So I need to find IB. And how am I going to find IB? Let's go back to this picture. Actually, we can find IB by doing Kirchhoff's voltage law around this mesh, the right mesh, KVL around right mesh will give this. So let's just go clockwise again. So we've got minus 3IA plus 4IB. Okay, now this time I didn't actually explicitly show you the voltage like I did there, but I'm sort of getting the idea that when I'm going in the same direction as the current, the voltage is going to be I times R1. So I don't have to keep showing the voltage. So it'll be IB times 4 equals 0. So it looks like IB is equal to 3/4, or wait a sec. Yeah, 3IA over 4, and we know that IA, what was IA? 3 amps, so 9/4. Okay, now that we know what IB is, now we can use current division. And I've got 30 more seconds to do it. And I can do it in 30 seconds because that's the beauty of current division is that you could just do it really quickly. I know that IB is 9/4 amps. And I know it's being divided among 3 resistors in parallel. So I'm just going to plug into that formula. So the resistance in this case it's that middle branch, the second branch, I2, is going to be a fraction of the total, which we just said was 9/4. And the fraction is going to be careful here, with current division you've got to take the conductance of the branch, so 1/8 over the sum of all the conductances. So there, you crunch out all those numbers and you get I2, which should crunch out to be 1.125 amps. And then you can get V1 in the same way. If you can figure out the voltage across R1 in this picture, you know that's going to be the voltage that's being divided amongst these branches, and so you can use voltage division. Okay. All right, see you next week.